All right. Good afternoon, everyone, and welcome back to the series of smart webinars. And we are in the internal presentation cycle. So today we have Dr. Hei Tang from Lawrence Livermore National Lab. She is part of the Atmospheric Earth and Energy Division at LLNL. Dr. Tang holds a PhD degree in petroleum engineering from Texas A&M University. She worked with Professor John Killow, who is very well known in the field of reservoir simulation and has made many contributions for just the development of algorithms that contribute to computational models. Right now, at the moment, she's just finishing up on task 4 of SMART, and then I presume she's also going to be part of SMART Phase 2. Her research focuses on data assimilation, deep learning-based surrogate model development for subsurface multi-phase flow, and uncertainty quantification. So today, she's going to talk about deep learning accelerated 3D carbon storage reservoir pressure forecasting based on data assimilation using surface displacement from InSAR. Lots of interlinked concepts here, but basically it's using the InSAR data as a proxy for pressure so that you have a higher resolution of spatial distribution of pressure, and then using that in conjunction with deep learning based proxy models to calibrate and forecast reservoir behavior. So without further ado, Hei.
Sure. Thank you, Shrikanta, for your kind introduction. And yeah, thank you everybody for being here. And it's my great pleasure to represent our Lawrence Livermore team to present some of our recent work for Smart Task 4 as to build deep learning accelerated data simulation workflow for pressure forecasting using InSAR data. And specifically, our team can have Peng Cheng and Chris and Joe Morris, and we also have hired two really brilliant interns last summer to help us with the work. Hongen from UT Austin and Sue from Stanford. And we also have support from our Geostatistical development team. So, okay, I will. So the motivation of Smart Task 4 is to build fast data assimilation workflow to forecast reservoir performance using machine learning approaches. And here I show a typical data assimilation workflow. So usually we will start with some initial guess of reservoir models. They may be facies distribution or permeability distribution, and they are represented by like discretized grid blocks. And that's no doubt in very high dimension, and we can maybe up to 1 million grid blocks to represent a reservoir. And then we need to reduce this parameter space that we want to calibrate, and so that it can be easier for us to update them in the optimization approach. And then what we do is that from our initial guesses, we will use some high fidelity forward model, mostly a reservoir simulator, to get predictions for pressure and saturation. And then we will compare with our observation data, usually acquired from 3D seismic, monitoring pressure, or in this case, we are using InSAR. And then we see whether our predictions can match with the observation well within a specific tolerance. If it can match well, we will go ahead to performance forecasting. And if not, we will need to use a kind of inverse model engine to help us update our parameter space. And then it's an iterative process and very computational intensive. So we want to use machine learning approaches to help accelerate this process. And mainly the machine learning approaches can take a role in 2 places in this workflow. And the first place is to to enhance the parameterization. So usually with some more advanced machine learning techniques, some neural networks, we can more efficiently parameterize the parameter space, and usually we can also do some more, also parameterize some more complex scenarios that used to be really difficult to handle by traditional parameterization approach. And the second part is like to reproduce the computational intensive high fidelity forward model with machine learning based surrogate. And this usually can significantly reduce the computational cost of this workflow, since this part is usually the most computational intensive one. So in this presentation, I will mainly introduce how our workflow work with this, the machine learning techniques plays a role in these two parts. Okay, so before going into the details of our new developed workflow, I want to give a quick recap of our previous work. Previously, for Smart Task 4, we have developed a data assimilation workflow for CO2 plume forecasting. And the main objective of that workflow is to use seismic inverse the CO2 plume and pressure history from a monitoring well to forecast future CO2 plumes and reservoir pressure at the same location. So for that workflow, we find that we can use unconditional 2.5D reservoir models to history match synthetic data from 3D reservoir simulations. And it's actually it's a really interesting work, and it has also been published last year on the International Journal of Greenhouse Gas Control. So you can find the details of the work here. And so based upon this work, we want to extend our capability. And the first thing most directly we want to do is that instead of predict for reservoir pressure at some sparse reservoir locations, we want to build a workflow that will be able to predict reservoir pressure spatial distribution. And also, since the reservoir pressure is more sensitive to the vertical permeability distribution, so we no longer want to use a 2.5 to calibrate a 2.5D reservoir model, but we want to calibrate a full 3D reservoir model. So we are still using the reference reservoir model that created by ERC to generate our synthetic data. This is a full 3D model that contains two facies, and it has 4 injection wells following a 2 million metric tons per year total injection target to inject for 10 years. I want to additionally mention that these 4 wells are actually connected to a single manifold at tubing head. So they are actually share a same tubing head pressure, and the injection rate will be allocated dynamically through the injection, throughout the injection period. So based on their injectivity. So it's actually a more complex boundary condition than fixed bottom hole pressure or fixed injection rate. And so we initially started with unconditional 3D reservoir model, just as what we did for the 2.5D workflow. And then we find that it's actually really challenging and maybe not feasible, since in 3D case, we are dealing with a much larger reservoir parameter space. And also this boundary condition tends to be specific challenging for the 3D case for surrogate modeling development, since this is kind of hard for our surrogate model to figure out these vertical connections and how they're rate allocated. So we finally decided to use conditional 3D reservoir models as our initial guesses. And we use virtual well logs from 9 wells to give us hard data to build the initial guesses of reservoir models. And I will go into the details of how our geostatistical modeling workflow looks like later. So we want to, in this workflow, our motivation is to predict for the spatial distribution of pressure. Well, this is challenging since we usually have pressure measurements from wells that are sparsely allocated spatially, and they are usually expensive to obtain, especially for carbon storage projects. So we are thinking whether we can use InSAR as low-cost, high-dimensional monitoring data. So the InSAR data are typically collected from satellite, and they are usually freely available. And by interpolating the phase measurements from InSAR during two paths at the same location, we can interpolate for the surface deformation in a millimeter resolution. This one pass usually takes several weeks. So it means that we can have surface displacement measurement at a relative high frequency, and these are really high dimensional monitoring data. So it will be really interesting if we can take advantage, we can make use of this data. And since we are dealing with synthetic case in phase one, so we are using in our modeling tool to generate synthetic InSAR data as well. And the process is to use the coupled flow and geomechanics simulation to get the surface modeled surface displacement. And we can see that this surface displacement is highly correlated with reservoir overpressure. So our hypothesis is that maybe it is feasible for us to use InSAR inverted surface displacement as observation data to infer and forecast reservoir pressure distribution. So to be specific for this case, we will want to use displacement data at 2 years as our observation data, and we want to forecast for reservoir pressure for the following years, like 2 years, 5 years, and 10 years. So based on this objective, here is our 3D workflow. And it mainly contains 3 major components. So model parameterization, data assimilation, and after this work, we converged with well matched with our observation data. We will then go to performance forecasting to forecast for reservoir pressure. And I will introduce this workflow in details part by part. So the first part is to have a good initial reservoir models as our initial guesses. Let's first take a look at the statistics of the reference model. I show the histogram of porosity and permeability. They follow by model distributions since we have 2 phases considered in this reservoir. And we also find through their cross plots that there are actually no simple one-to-one correlation between porosity and permeability. This is just like what most of the cases that we will deal with in the real field. So keep this in mind. We developed this our current geostatistical modeling workflow. The first, we will extract hard data from our this virtual wells, and then we will add measurement arrows to the hard data. And for the facies distribution, we use sequential indicator simulation to generate facies model. And for the porosity and permeability, we will use 2 sequential Gaussian simulation to generate normalize the porosity and permeability fields first. Notice that here we are using the same random seed for these two sequential Gaussian simulation so that they can automatically generate porosity and permeability fields that dependent porosity and permeability fields. And then we will rescale this normalized field based on facies to get the final porosity and permeability distribution. Here I want to add a word here for why we choose to use nivels. We actually did quite a bit experiments on here. We find that if we only use hard data from fall injectors, the sequential indicator simulation will not be able to give us reasonable facies distributions since we are dealing with a really large reservoir and the fall data points are really like sparse to constrain this field. So we finally find out that we will need more wells to constrain this facies distribution. And there may be some room to improve this geostatistical modeling approach, and you are welcome to let me know your thoughts and comments. Okay, so now we have our initial reservoir model distribution, and we can find that in this reservoir model, in each reservoir model realization, we will have three-dimensional fields. So it's a really large parameter space, and we want an efficient method that be able to significantly reduce it. The major difficulty in parameterize this field is the facies, is how we parameterize facies distribution, since it follows a binary distribution, and this traditional PCA approach will not work for it. And so we actually tried several methods in the literature, including GAN, VAE, and we finally find that the CNN-PCA approach proposed by Dr. Dolovsky's group is the most reliable one, at least for our task. And the basic idea of this approach is to use a convolutional neural network as a model transform net to post-process the PCA and to get the final CNN-PCA realizations that follow in the original binary distribution. And this model transform net, they were borrowed from some pre-trained computational vision network, and you can find the details in their previous publication. And we basically find that we basically like this method is because we do flow testing on different methods, and this method gave us the best flow testing results, which means that it honors the flow behavior of the previous realization of the initial ensembles the best. So we now have a method to allow us to reduce the facies distribution to a lower parameter space, and we can also generate new facies distributions from a lower latent parameter space. And then what we should do for the porosity and permeability distribution is like we follow the same logic as we have done for our geostatistical modeling, and we build a single PCA model for the normalized porosity and permeability field combination, since they are dependent. So we build a single PCA model for it. And so then we are able to generate from a latent space a normalized porosity and permeability together. And then similar as the geostatistical workflow, we will rescale it based on the different facies distribution to get our final porosity realizations and the final permeability realizations. So in this case, we can efficiently reduce our parameter space from around 100K to 1K, which is a significant reduction in this case. Okay, so we have built the parameterization model part, and now let's come to the surrogate model part. So in this workflow, we need to develop two surrogate models. One is for data assimilation workflow, which allows us to quickly predict for the surface displacement to compare with the InSAR data. And the other is the performance forecasting part, where allows us to predict for the reservoir pressure distribution based on the calibrated posterior reservoir models. And here we are using the same network, neural network structure, but training them by different data sets to build these two surrogate models, since they following the same 3D input and 2D output structure. And I will use the surface displacement one as an example to introduce it. So we developed our surrogate model based on a 3D to 2D UNet, residual UNet structure. It is modified based on a traditional UNet structure, where that structure is like characterized by these concatenation layers between encoding network and decoding network. And since in this case, we have the specialty to deal with 3D input and 2D output, so we modify the architecture a little bit. We add a reduced mean layer before the concatenation layer. It allows us to reduce the 3D feature maps to the 2D feature maps and then be concatenated to the decoding network. We did try different methodologies to reduce this dimension, the 3D dimension, and it turned out the reduced mean is the most efficient one. We in total generate 3,000 reservoir models from CNN-PCA approach for the model training, validation, and testing. And we run high fidelity predictions with the Geostatistical simulator. So we evaluate, so in training the reservoir models, we evaluate 4 different sizes for training from 1,000 to 6,000. And we will test the model based on 100 holdout reservoir models. And for the displacement model, we find that we will need around 4,000 training realizations to achieve a good model prediction accuracy with R-square like larger than 0.98. Well, for the pressure model, we find that we need a little bit more data, like we will need around 6,000 data to achieve similar model prediction accuracy. Here I show like our model performance based on testing data set. We sample several realizations from the testing data set and organize it from low R-square value to high R-square value. And in the first row, I show the true displacement field. And then second is our surrogate model prediction, and the third row, the difference. We can find that in general, the model have really good performance for all this, for a wide variety of scenarios. Well, for the realization one, we did see some like underperformance because it's a really rare case in our training data set where this injection will take almost no injection due to the poor vertical connectivity. And this is our predictions of based on the our predictions with time. And since we trained the model use training data within 10 years of injection, so there is no doubt that we have really good in interpolating performance within these 10 years. And the model also have a moderate extrapolation predicting capability for up to 16 years. Okay, so now we have introduced the major components in this workflow, including the geostatistical modeling, parameterization, and surrogate modeling with the deep learning neural network. So we choose an inverse model engine called ES-MDA, which is an ensemble-based method very popular used in our field. And it's mainly famous for its capability to be able to match the history data well, since it can update the parameter space for several iterations based on the perturbed observation data. And we, in this case, through some trial and error process, we find we will need around 100 ES-MDA ensemble and 12 ES-MDA iterations to achieve good history matching results. So here I show our calibrated surface displacement field. And since we are using 2 years data as the calibration, so it's no doubt that we can have a good match with the 2-year data. On the first row, on the first column, I show the the mean and standard deviation of the surface displacement prediction based on the prior ensemble. And on the second row, I show the mean and standard deviation of the surface displacement based on the posterior ensemble. And they can match with the true well, since it's being used for the calibration. And then we forecast for the displacement prediction at 10 years. And we can see similarly, we can have a good prediction results based on our posterior ensemble and with much reduced uncertainty. And here I show some calibrated 3D reservoir models. I show several realizations from our prior realization ensemble and also some correlated realizations in the posterior ensemble. And here I also show the reference model for comparison. So in the prior ensemble, we did consider a wide variety of facies distribution. And then although after calibration, the posterior realization are not exactly the same as the reference model. We actually can never achieve that, but it does have more similarity with the reference model and with much less variety compared to the prior ones. And finally, I show this depth average the pressure forecasting at 2, 5, and 10 years. On the first row, I show the true results simulation true pressure field from simulation, and also I show the mean and standard deviation of our pressure predictions based on the posterior ensemble. And we can see that in general, we can have a really good pressure forecasting for the current year and as well as the following injection years. And we have therefore achieved our initial design objective of this workflow. And finally, the most important part is I summarize our computational cost of this whole workflow, since the main purpose of using machine learning techniques is to increase the efficiency of the workflow. And we find that the whole workflow can complete within 30 minutes on a local personal computer. Well, if the traditional workflow using a reservoir simulator will cost about 3,000 CPU hours. So there are about 1,500 times speed up here, which is a significant improvement. And we do need to, this speed up does need some previous work, some previous computational cost. Say like we need to build training data sets, and it costs some time, and also we need some GPU time to training the data set. But this will all be the previous work and not counting inside the workflow computational time. So the whole workflow can run fairly quick. And finally, I want to summarize my presentation. So we developed a 3D data assimilation workflow for reservoir pressure forecasting, and we demonstrated the efficacy of using InSAR data as monitoring data to infer reservoir pressure buildup. And we applied deep learning techniques to significantly improve the efficiency of this workflow. And we have also prepared a paper and have submitted to peer review process. So that's all of my presentation, and your comments and questions are warmly welcomed.
Thank you. And now for our participants, if they have any comments, questions, observations, and related thoughts, we invite you to share them. David, I see your hand is raised if you want to unmute.
Yeah, interesting presentation. I'm just wondering, have you started to consider other data types besides InSAR for implementing in your algorithm? Because a lot of the Midwest, where a lot of carbon storage goes on, really doesn't work too well with InSAR because of, it's farm fields, it's covered with snow part of the year. So InSAR isn't maybe the best option in those cases. So I just want to see if you start to look at other data types to use.
Yes, thank you for your question. Yeah, we do agree that in this workflow, we consider a very ideal scenario. We use synthetic data, added Gaussian noise, but in reality, we can expect many noise in the InSAR data, and it can be maybe in some scenario, it's really difficult to interpret from InSAR to get a good displacement field. So to answer your question, we did consider other data type. For example, in our previous work, we have considered using those CO2 plumes inverted from seismic data, and also the pressure from monitoring wells. And this can all be considered. And so InSAR, yes, it's kind of tricky. If we have good InSAR data, then we can use it. And if not, we will probably need to rely on the pressure measurement from monitoring wells to calibrate the reservoir pressure. Yeah.
Yeah, hey, Srikanta here. Yeah, just echoing what David said, nice presentation. But I think the main concern is really the availability of InSAR data. And in fact, I wonder if you have taken the time to look at ongoing CCS projects to see how many of them collected InSAR data and how many of them were able to correlate the InSAR data with the underlying pressure changes. I know that this was done for InSAR, but other than that, at least I'm not aware of any other CCS project where a successful correlation with the InSAR methodology was done. So while your approach is very nicely developed and well demonstrated using synthetic data, I'm not sure about the broad applicability if InSAR is not available.
Yes, I think it's really it's a reasonable concern. Yeah, string content. And so to be honest, from my literature search, since I also need to prepare for the introduction of my paper, and mainly successful applications, as you said, is from InSAR carbon storage project. And so as for the InSAR availability, I think we should consider it in two aspects. First is like whether we can have good engineering approach to deal with those noisy InSAR data, like to inverse for a good surface displacement. And I think there are certainly there's room to improve this. So to denoise, distrain those InSAR data to give us some good surface displacement data. And this does need effort, but it's achievable through some, for example, since this InSAR data, they are really high frequency. So I did see in the literature, there are methodologies like to average the InSAR data in a full year span so that they are able to get good quality InSAR data for like at least representing that year. So this is one aspect of SOS. And the second aspect of SOS is like InSAR data, I think, yeah, that they are available everywhere. There is no doubt. And we did have other projects, not carbon storage project, but like we have project with California State. For those oil fields in the South California, they have a really like abundant. They have a lot of InSAR data, and we also have scientists have experience in dealing with this InSAR data to do some analysis for steam injection and some other like surface expression cases. So yeah, I'm optimistic about this, and they do have a lot of challenges to solve. Yeah.
Hui, if I could add a couple of thoughts to this as well.
Yeah.
You do bring up. It is a fair comment that in general for existing historical CO2 storage, the one example that comes to mind is InSAR. I think it's good that you pointed out some other cases, though, like in the future as CO2 sequestration is applied more broadly, I think we are going to see it used again in locations where InSAR quality is much higher, such as we've seen it used to monitor geothermal and, as you pointed out, oil activities. The other point, though, was just to re-emphasize a point you made earlier, which is that you have developed workflows where the focus was on, other data that is, we've seen generally available for CO2 storage, such as wellbore-based pressure measurements and 3D seismic. So this is just one particular workflow of a suite that you've been working on, and you've worked with the other data types as well.
Right. I think the advantage of something like this is basically look at your primary monitoring network and realize that it's extremely sparse with just a handful of monitoring wells from which you're going to get pressure data. So how do you supplement it in space? And the only way really at which you can take your limited pressure data and sort of supplement it with some surrogate is using InSAR or something like that. Just as you have limited saturation measurements, and then you supplement it with the saturation-based proxy that you get from your seismic. So the question is that if you only had, let's say, 9 wells from which you are monitoring pressure, let's say 4 wells, then what are the limits of applicability of these kinds of algorithms? So maybe that's one of the questions we pursue in phase 2 as we look at, say, a site like the IBDP project, where there is, 1 deep monitoring well and 1 injection well. So that's all that we have. And in that realistic setting, what are the limits to which we can take these advanced inversion algorithms? Because obviously there will be an impact on the resolution that you can achieve.
Yeah, we definitely need to be able to bracket that and understand it. Yeah, I agree. Yeah. It's something we can we should focus on early for phase 2, as you suggest.
Yeah. Regarding this Hongkyu from Zambia, and regarding those, regarding actually IBDP sites, obviously, yeah, we don't have really InSAR data yet, but wonder whether we can link to some kind of some fiber optic, distributed fiber optic data that's shallowly installed. So that may be interpreted to kind of give us some other information to reflect certain response upper bound of Reservoir unit. Another aspect we probably need to think about regarding phase 2 activity, in particular this work package 2C3, is in terms of risk management, and most of induced seismicity occurs basement rather than surface. Obviously, if we're really aiming at a gigaton type injection scenario, we should look at some upper part of the reservoir response. But obviously, regarding induced seismic, most of actually induced seismic occurs mostly kind of through the basement. So I think the framework itself can be applicable, but probably data set kind of I'm seeing from the exercise may not directly applicable. And the other question and comment is using PCA linear dimension reduction, and nowadays through machine learning exercise, we see a lot of nonlinear dimension reduction method, quite a bit, and that typically perform better than linear based dimension reduction. Also, we can reduce dimension much significantly compared to PCA method, such as NDI, we use some variation autoencoder or WGAN to reduce our dimension. It performs much better, and then it captures features much better since you're showing you reduce dimension to 1,000, which is quite actually a high number in reduced space. So maybe that's kind of, we can work together to improve those aspects, but that's kind of comment and questions.
Yes, thank you, Hongkyu. We do have explored GAN, at least GAN on our side, and maybe we have some. Maybe our neural network is not developed that advanced, so we do observe some issues in using GAN, like the flow behavior is not really good. It can not really represent the initial realization. Say we do reservoir simulations on this initial ensemble, and then we do another set of reservoir simulation on the ensemble created by GAN, and then we find that the flow behavior not really being honored well. So we do find some issue in implementing it, and maybe we can have a follow-up meeting to discuss further. Yeah, that will be of interest. And I do agree with you. Yeah, this is not a really significant reduction to 1,000 parameter space. And maybe with GAN, we can do like 200 latent space variable. It's possible. Yeah.
Yeah, I mean, GAN is kind of tricky to optimize, even difficult to optimize because of longer training time. But standard GAN may not work very well for our problem, but certain types of GAN, like some kind of DC GAN or W GAN, which using different actually loss function to learn the features much better, and then outcomes kind of more controllable, although kind of algorithmically it's a little still kind of need to study more. But yeah, I think there are potential algorithms we can explore together.
Yeah. We can do work on this together.
Rylan, your hand is up. I think you're muted still.
Can you hear me?
Yes.
Oh, okay. Okay. Yeah. So, it's kind of echo. It's fine. It's weird. That's fine. So, so my question is, let me take off my headset. Sorry. How about next people ask the question? Let me fix my audio easier. It's kind of echo.
We lost your sound again.
Yeah, so I have a quick question in between here. Thank you
Sure.
for the great talk. Really enjoyed it. So my question is, for the model that you just presented, what is the depth of the reservoir below the ground surface, and what impact might that have on the InSAR relatability?
How the depths below the reservoir? Sorry, I forgot the exact number. I think it's at least more than 2,000 millimeters. So the depth is. You can find this information in my paper. I cannot provide the number. No, sorry, I forgot it. And in terms of the InSAR, how this influence InSAR, actually from our simulation, we find what influenced the InSAR like magnitude most is like the geomechanics properties, the back modulus, this kind of Young's modulus of the formation layers, like above the reservoir. So these are some parameters that will influence the InSAR magnitude, and these are fixed in our case. So I know there do some other works will also make these variables to be tuned to match with InSAR data. Yeah.
Bill Harbert. Oh, go ahead, Bailan.
You can hear me now, right? Good. Yeah, sorry, I have some problem with my audio. So okay. So we very nice walk. I have a few questions. So the first one is about the observational data. So you consider the surface displacement, right, as your observational data in your data simulation workflow. Is that right?
So could you repeat your question, Bailan?
So you use the surface displacement as your observational data, right?
Yes.
Yes. In your at the beginning, you mentioned that you can use the surface displacement data to get the pressure kind of images, right, for the storage formation. So I'm wondering, are you considering the pressure imaging in your history matching, or just the displacement?
So in my history matching algorithm, I just use displacement data as the calibration data, and the pressure, I didn't use any pressure data. They are just as a testing metrics to test for the calibrated model.
Yeah. So I'm wondering, you have the surface displacement kind of data, right? So how the pressure change can be reflected by this kind of displacement, surface displacement data. So I'm just curious about this kind of things.
It's mainly due to the the physical process. So the surface displacement is mainly caused by the overpressure in the reservoir, and you can imagine it as a cat in the quilt. So since there is some overpressure in the depth reservoir, and then those upper formation layers are like a quilt, so they are correlated, this surface displacement and the overpressure in the reservoir, but they are correlated but not linear directly correlated. So we can use yeah.
I'm just wondering, is the question perhaps how the correlation was done in this workflow? Because you did develop the model that mapped from the pressures to the surface deformation, right?
Yeah, so it's like a one-way coupled workflow. So I will input the overpressure to the geomechanics model to get the surface displacement.
Okay. Yeah, so that means, so for your the reservoir model, you build a model from the surface, right, to your kind of storage formation.
For the reservoir for the reservoir model, like overpressure, I only use the reservoir layer to do the reservoir simulation to get the pressure the overpressure of the reservoir. But for the geomechanics model, I do need a full-scale simulation, like simulate from the top to the bedrock beneath the reservoir to get the surface deformation.
So you originally start from the over pressure, right? The build-up pressure, right, from the reservoir, then invert that to kind of get the InSAR or this surface displacement, and then use that as observational data.
Yes, yes.
Oh yeah. So if you have the pressure build-up information in the storage reservoir, yeah, you probably can directly use that as your observation data in your pitch matching. Not need to go to the displacement observational data and then go back to the pressure prediction. I think, yeah, that's just my thought. I think we also done a lot of work just directly using the pressure images to do data simulation. Yeah. So
yeah, I think it's just our. I agree with you. It's just our assumption, like from where we start to use observation data. Since actually surface deformation is also not the raw data. The raw InSAR data is like phase measurements and those. So we are assuming that we can get a good surface deformation from those raw InSAR data. So maybe for your case, you are assuming that we can get a good overall pressure map from those displacement inversion and those from this displacement, we can get a good pressure map. So yeah, I think that's basic different assumptions of the workflow. Yeah.
Okay, so my next question is about the comparison or benchmark. So this one is based on it's kind of based on pressure measurements. And have you compared this with the CO2 plume images?
No, I haven't compared it with CO2 plume images.
Okay, yeah, that may be a good comparison. Yeah, to see how good this kind of data is for you for the prediction. Yeah.
Yeah. So yeah, I assume that if we want to get both good predictions on CO2 plume and pressure plume, we may need to incorporate both data sets to calibrate the reservoir model. And it will be a more challenging task, and it probably will be the next step.
Yeah, I think that's an excellent point, Bali, and yeah, Hewei, I would really strongly encourage you to go back and look at the saturation distribution that you got from your GeoX simulations, and then compare it to the calibrated models prediction. And if you did an ensemble average, then maybe that ensemble average saturation distribution should be predicted to what you put in or what you got in the GeoX model. Because ultimately, when we go to the regulator, we will use models like this to predict the evolution of the CO2 saturation in addition to the evolution of the pressure. So in a way, that's really a very blind test type validation of your approach. So, you don't have to do any extra simulations. You just have to grab the output. And I would strongly encourage you to add that to your report or your paper.
Okay, sure.
Yeah. Yeah, I have a few other questions, but I can talk with you, offline. I will leave some time for other guys. Yeah, thank you.
Thank you.
We did have a question that came through in the chat. I know we only have a few minutes left. It's from Bill Harbert. In your reservoir forward model, did you assume permeability anistrophy? I might not be saying that correctly. Vertical permeability being less than horizontal permeability. Could you estimate this anisotropy from future development of your approach? Let's start there.
Let me
see if I can copy this into the chat as well. There.
Did you assume? Yeah, we did assume permeability and isotropy. So the vertical permeability is like 0.1 of horizontal permeability. And can you estimate this from future? Can you estimate?
I guess Bill's question is really, did you treat the anisotropy ratio as a known quantity or as an unknown quantity? Because that is typically one of the bigger uncertainties, and we just assume that it is something like 0.1 to 0.3. But can you back that out of your calibration process if you use that as an unknown parameter?
Yes, it's a good point. Yeah, I have never thought about this. It's just like, a known input in my simulation, and I never thought about like this can be changed. Yeah, it's a good point.
Depending on the reservoir, it'll have a strong influence on the degree to which you see vertical versus lateral development of the plume. So you might be sensitive to it if it's a thick enough reservoir.
Yeah. Yeah, this is a reasonable point.
And then a follow-up question, is InSAR being used routinely for gas storage modeling?
Routinely for gas storage monitoring. I think based on what Srikanta and us has discussed before, at least for carbon storage, it might not be used that frequently because it does have some it does have some restrictions. For example,
Right. But I think he's asking about underground natural gas storage. And there are lots of natural gas storage reservoirs. So maybe that's something to look into is, what kinds of monitoring techniques are used for underground gas storage type applications. And Joe, I'm sure that there's somebody at Livermore who's worked on underground gas storage projects and would be able to put Heve in touch with the appropriate people.
Yeah. I just did a quick search and Don Vasco's name pops up as somebody who's, of course, who's done it.
Yeah, of course. All right. Well, we are at 3:00. So thanks, Heve, for a nice presentation, and thanks everybody for a good follow-up discussion. And this is the kind of discussion that we want as we continue our progress for Smart Phase 2. So thank you, everybody.
All right. Thanks, everyone.